NoSQL was invented to replace SQL. It wasn't. The term NoSQL was coined in 1998 for a lightweight relational database that simply removed SQL as its interface. Not to escape relational design, not to abandon consistency guarantees, just to simplify an interface. The modern non-relational movement came a decade later, and it emerged not from frustration with SQL, but from a deliberate architectural choice made by two of the largest distributed systems on the planet. This is no-tech. And this is the story of a debate that was never quite what it seemed. To understand where NoSQL came from, you have to start in 1970. Edgar Codd, a computer scientist at IBM, published a paper that would quietly reshape computing. Its title was dense. Its implications were enormous. Codd proposed organizing data into relations, tables with rows and columns, where every piece of data could be linked to every other piece through keys. He called the theoretical framework relational algebra. What Codd built into this model were guarantees: atomicity, consistency, isolation, durability, what we now call ACID. The idea that a database transaction either completes fully or not at all, and that the data you read is always trustworthy. For the next 3 decades, this model dominated. SQL became the language of enterprise data. Banks, hospitals, airlines, any system where correctness wasn't optional ran on relational databases built on Codd's foundation. The model worked. But the internet was about to ask questions it wasn't designed to answer. In 1998, a developer named Carlo Strozzi released a project he called NoSQL. The name meant exactly what it said: NoSQL interface. The underlying data was still relational, still structured. Strozzi simply wanted a lighter way to query it, without the SQL language overhead. This project went largely unnoticed outside niche circles. The name NoSQL sat dormant, and for 8 years, the relational model remained the unquestioned standard for serious data storage. Then, in 2006, Google published a paper, and in 2007, Amazon published another. These 2 papers didn't reference Strozzi. They didn't claim to be NoSQL, but they described distributed data systems built on a fundamentally different philosophy, and they changed the conversation permanently. Google's Bigtable was built to handle planetary-scale data, the kind of volume that comes from indexing the entire web. Amazon's Dynamo was built for always-on availability, the kind of reliability that comes from running one of the world's largest retail platforms. Both systems made the same core trade-off. They relaxed ACID guarantees in exchange for horizontal scalability. BASE stands for basically available, soft state, eventually consistent. It's not a failure to achieve ACID. It's a deliberate philosophical shift. The system will eventually reach a consistent state, but at any given moment, different nodes might return slightly different answers. For Google's search index, this was acceptable. A slightly stale search result is better than no search result at all. For Amazon's shopping cart, a brief inconsistency between regional data centers was a reasonable price for never going offline. The developer community noticed. When these papers became public, engineers started building systems inspired by their architecture. Cassandra, CouchDB, and in 2009, MongoDB. Strozzi's dormant term got repurposed. NoSQL now meant something it never originally described: non-relational, distributed, base-oriented data storage. The movement was real. The naming was an accident of history. Around the same time these distributed systems were being designed, a computer scientist named Eric Brewer formalized something that engineers were already discovering in practice. In 2000, Brewer conjectured what became known as the CAP Theorem at the PODC conference. In 2002, Gilbert and Lynch formally proved it. The theorem states that a distributed system can guarantee at most 2 of 3 properties simultaneously: consistency, availability, and partition tolerance. This framing, pick 2 of 3, became enormously popular, and it was widely misunderstood. Here's what the proof actually says. In real distributed networks, network partitions happen. Nodes lose contact with each other. You cannot engineer partition tolerance away. It's a physical reality of distributed systems. So the real choice isn't 3-way. When a partition occurs, you face a binary decision. Do you maintain consistency, refusing to serve requests until the partition heals? Or do you maintain availability, continuing to serve requests, accepting that some answers may be stale? CP systems prioritize correctness. AP systems prioritize uptime. Both are valid. The choice depends entirely on what your application can tolerate. The early NoSQL movement largely built AP systems. That was the point. Availability and partition tolerance matched the use cases: social feeds, product catalogs, session data, where eventual consistency was a reasonable trade-off. But the story didn't end there. In 2012, Google published the Spanner paper, and it directly challenged the assumption that horizontal scaling required sacrificing ACID. Spanner achieved global horizontal scalability while maintaining full ACID compliance. The mechanism was extraordinary. Google built TrueTime, an infrastructure using atomic clocks and GPS receivers to synchronize time across data centers with bounded uncertainty. This allowed Spanner to order transactions globally, without the consistency compromises that distributed systems had previously required. This wasn't a small refinement. It demonstrated that the SQL versus NoSQL trade-off wasn't inevitable. It was a design choice, made at a specific moment in computing history, with the tools available at the time. Meanwhile, the NoSQL ecosystem was quietly converging back toward the guarantees it had originally abandoned. MongoDB, by 2018, added multi-document ACID transactions in version 4.0. From MongoDB's release in 2009 until version 4.0 in 2018, applications had to implement consistency logic themselves, in application code, not in the database. That complexity was real. The engineers who built those systems in the 2010s understood the trade-off they were accepting. The SQL versus NoSQL debate was never about which approach was better. It was about which trade-offs were worth making, at a given scale, for a given use case, at a given moment in the history of distributed systems. Codd's relational model gave us correctness as a default. Bigtable and Dynamo gave us scale as a default. Spanner showed those defaults weren't mutually exclusive, just expensive to combine. Modern systems often use both philosophies in the same application. A financial transaction goes through a relational database. A user's activity feed comes from a distributed document store. The architecture reflects the trade-off, not a winner. What the SQL versus NoSQL decade actually taught us is that every architectural decision is a bet. A bet about what scale you'll need, what consistency you can afford, and what your users will notice. Those bets are still being placed today. I'm here to help you know the systems that shape how data moves. If you've navigated a SQL to NoSQL migration or built consistency logic at the application layer before MongoDB 4.0, what surprised you most? Share your experience below. See you at the next schema.